I'm Jack St. Louis and Jim Bosek from the Vermont Astronomical Society. Please help me welcome them.
Hello, glad to be here. Yeah, I'm Jack, and I'm the current president of the Vermont Astronomical Society, and May 6th is when we turn 60. Wow. It turns out to be the same day the club started, is the same date. That's kind of cool. And we're down to, at one point, to 3 members. We're now to about 100 or so. That's kind of nice. And we're spread out throughout the upper part of the state. We even have members in New Jersey, who's a retired astrophysicist, a nice grandma lady, she's great. And somebody way out in Oregon. And we have people way up north and some down south. And it's just a good group of people who just enjoy sharing their passion for the night sky, or daytime sky even now, with everybody who wants to listen to us. So Jim's going to do the presentation. I was going to, but my voice is fighting me, so I'm not going to do it. He does a good job, and just let him go. Go ahead.
Great. Okay. So my name's Jim. They picked me as the Eclipse chairperson, the Eclipse committee chair. That really isn't a big deal. But the eclipse is a big deal. None of us here will probably get another chance unless we want to spend a lot of money traveling to do it. So take advantage of whatever you get. We're going to talk about a bunch of stuff. We're going to talk about the sun a lot. The moon causes the eclipse, but this is definitely the sun's show. There's no doubt about it. We're going to talk about the timing of the event, why it happens, where you need to be looking, but it's pretty easy to find the sun in the sky, so usually, but where to look, what to expect when it happens. That's kind of important because it's a special event, and we can talk about it in relationship to other normal things like a sunset or a sunrise, but it's not quite the same. And how to do this safely. Nobody wants to hurt their eyes doing this, guaranteed. There's some, I'll call them wives' tales about it. You know, just use your head for something besides growing hair is what my dad would say. And let's start with the sun. So, like I said, this is the sun's show, and this is an opportunity to learn about the sun. Not just here, but this is what science is going to be doing. We're still using these eclipses to learn all we can about the sun. And the sun is powered in this chunk in the middle that's called the core. And it's like a continuously running hydrogen bomb. It takes the helium from the sun and smashes it together and makes it into, or takes the hydrogen from the sun, smashes it together and makes helium. And the energy that is the result of that reaction is what's powering the sun. Here we have what we call the radiative zone. It's kind of like a pressure cooker. And there's really no nuclear reactions going on there, but it's not physics like we have on Earth at all. And it takes millions of years for that energy of the core, the energy, the heat and light, to make its way through that radiative zone. The core is about 27 million degrees. The radiative zone is thought to be about 17 million degrees. And then we get to this area here, the convective zone, where the physics becomes a little bit more like we have on the Earth. And it's like a big pot of boiling oil, is really what it's about. So as the stuff is heated down here near the radiative zone, it rises up to the surface of that, it cools off and falls back down. Kind of like having a radiator in your house, constantly circulating the hot air. I like to think of it like a pot of boiling oil, because when you get a close look at it, that's what it looks like. Here's a diagram of that pot of boiling oil, and we'll see a picture of it soon. So the stuff rises up, and you get these bright spots surrounded by, looks like a little bit darker areas where things are cooling off, and they sink back down. All those bright spots you see are about the size of Texas. So you're going to see it close up here in a moment. There it is. And there's those spots, the hot spots on top. All of them are roughly the size of Texas. The slightly dimmer areas around it where it's a little bit cooler and it's sinking back down. Here's a picture of that surface of the sun, the top of the disk of the sun, the convective zone. That's all the stuff we're seeing when we look at the sun through special devices. We don't look at this just with our eyeballs, because we won't look long. So when we filter it out right and look at it through proper devices, we can observe this area of the sun. And you can see it now has sort of a grainy look to it. That's from all those spots the size of Texas. You notice we got these storms of sorts. They're called sunspots, and you notice they're all in pairs. They like to show up in pairs. Not necessarily exclusively, but the vast quantity of them will show up in pairs. And we'll see why in a minute. Here's a close-up of one of those sunspots. So it looks dark here in the center. We call that the umbra, just like we talk about the center of the eclipse as an umbra. We have this area around it that's a little bit brighter. We call that the penumbra, just like an eclipse. The partial, where people are in the partial, they get the penumbra. I like to point out right now that this fuzzy area is going to look like something else we're kind of familiar with if we've taken junior high science classes. These storms are magnetic in nature. And this is why they occur in pairs. This is why you see it, this penumbra around it. We'll get to that in a minute. How big are the sunspots? They're big. Right here between the two arrows is the size of the Earth. And the Earth could fall into one of them sunspots like somebody walking into a manhole in the street. They look dark. That's relative. One of these, this sunspot right here, if you could isolate it and put it in the night sky, it'd be about as bright as the full moon. So that darkness is relative to the rest of the disk of the sun. I'm sure almost everybody here already has a pair of eclipse viewers. Yeah, a lot of people have them already. If you take your eclipse viewers and there's a sunspot this big, you're probably going to see it through your eclipse viewer, if there's one that big. What else can I say? Not much about that one yet, but here is why we get them in pairs, because they're like horseshoe magnets under the surface. So we have a North Pole and a South Pole, and that's what we have there. Notice the fuzzy, these are the iron filings we put on a magnet. You might remember that trick from junior high. Notice it kind of looks like that penumbra a little bit, doesn't it? Also notice how the material follows those lines of force around the magnet, and you're going to see that evidence of that happening on the sun. Here's a diagram of a pair of sunspots and what's going on. So that horseshoe magnet's under here. Here's your sunspots. And here's magnetic fields trapping the gases coming from the surface like those iron filings in the magnetic fields of force on the horseshoe magnet. Here's a diagram of those magnetic fields on the sun. They're kind of like weather is on the Earth. So the weather you might call the solar weather is magnetic fields and their byproducts. We have high and low pressure areas on the Earth, and the sun has magnetic fields. It takes about 25 days for the sun to spin on its axis. And we know that because we followed sunspots across it and timed it. And if the sunspots are big enough, they sometimes survive and pop out again after they get around the back of the sun. The sun rotates on its axis differently. I believe it changes speed from the top to the bottom. It's like winding up like a rubber band almost. So I'm trying to remember. All of it escapes you when you want to remember it. When The sun takes about 25 days, and in other areas, I believe the poles take, I'm trying to remember which way is which now.
29.
29 days at the poles. So this is all winding up like a rubber band, so to speak. And here's what happens. This is a diagram of sunspot observations. And we realize the sun operates in an 11-year cycle. And this is a diagram of the sunspot activity over the course of years. Up and down. Some are higher, some are more active than others. And lately, the activity on the sun, even though we're supposed to be in a maximum, hasn't been quite as active as 40 or 50 years ago. Things are a little bit quieter right now. We have a quiet area here they call the Dalton minimum. The red is an area where we couldn't observe the surface of the sun as well. We knew of sunspots, but we really didn't have good ways of tracking them or seeing them. You pretty much had to look through see the sun through a dust storm, maybe down on the horizon on a real hazy day. You know, you're kind of risking your eyes even then. But it was good enough that they observed the sunspots and had some inkling that there was highs and lows even then. And in this area, between about 1650 and the early 1700s, we had something they called the Maunder minimum, where there were almost no sunspots. And this corresponds to a historically somewhat cooler era on the Earth that we now call the Little Ice Age. Uh-huh. And if we look at paintings of winter scenes from this era, they don't look like anything like we got now. There's supposedly some picture of London back then and people ice skating on the Thames River. And I don't think the Thames River freezes anymore. Not even in our more recent stuff, but not even for the last 150, 200 years. Here's how we study the sun. Here's how we like to study the sun, anyway. Newton told us if we pass light, showed us how when we pass light through a prism, we can separate it out into its colors, into its spectrum, its emission spectrum. And we study this emission spectrum from one end to the other, but we like one area in particular. And it's over here in the orange-red zone. We call it hydrogen alpha light. It's the light that comes off the sun due to all the hydrogen on the sun. And that is right here. And in this little narrow slot is where we photograph the surface of the sun. That light represents less than 1% of the output of the sun. We study all of this, but this is where we like to take our pictures. We don't necessarily take photographs of the rest of this. We measure it, its intensity, but we like the pictures right here. That's where we like them. And there's a picture of the sun in the hydrogen alpha light. So you can see all those little Texas-sized areas. These are flares, hot spots, areas where things may be slightly cooler. Prominences. We really can't see these well at all. It's hard for us to see them. Historically, it was only during total eclipses that you could observe this stuff coming off the sun. This is the only time historically when we could observe the chromosphere of the sun or the sun's atmosphere. In more recent times, we've developed ways to do this. But if you go back over 100 years, the only opportunity science had was during a total eclipse. Here's a picture of a prominence. And it's like those magnetic, just like this is probably coming off a pair of sunspots, just like those iron filings on a magnet. The magnetism is the electromagnetic forces are pulling the material off from the sun. There's no iron there, but everything's a plasma now. So things aren't quite on the rules of Earth. Plasmas are gases, but they're highly energized. The electrons and the nucleus of these atoms of gas are not bound together so tightly. Things are different. This is one of science's ways of studying this. This is an artificial eclipse. And that white line represents the true size of the sun. This is how much extra we have to pull away, have to shade it out in order to get any information at all. And a lot of those prominences are in this area where we're not able to see. Once again, this is why we like this opportunity of a total eclipse. Here's a prominence. Here's a good one. These are known as coronal mass ejections, where the sun literally pulls the magnetic fields on the sun literally pull the material off the sun and direct it out into space. We are really interested in studying these, as you're going to find out in a minute. This is not something that modern society really wants to play with or ignore. On September 1st, 1859, a coronal mass ejection hit the Earth. A good one. Our only electric and electronic devices at the time were the nascent technology of telegraphs. That was it. And it wreaked havoc with our telegraph lines. It's the electrical currents induced in the wires by the magnetic fields literally snapped telegraph wires, burned down some offices, electrocuted a few telegraph operators, and for a little while, the ones that were still going were able to operate their telegraphs without the batteries hooked up. Ouch. Can you imagine what would happen today? What would happen to our cell net? What would happen to our satellites? What might happen to that computer that's running your car? Some estimates say that it could be up to 10 years before we would fully have our electrical power grid back up. So this wouldn't be like a wet snow that put your power out for a week. This could be really trouble. We're watching for this now. One of the things we want to study, if we can, is coronal mass ejections. You know, there's a lot of them, but they're not all pointed directly at the Earth like looking down the barrel of a gun. In March of 1989, a coronal mass ejection associated with this huge sunspot whacked the Earth and put the power grid out in Quebec. And my guess is the reason it put it out for 9 hours, like you see up there, is it took them a long time to figure out what happened and to bring it up slowly. When you have a power outage at your home, the power company usually wants to tell you, shut everything you can off, because they don't want to bring it up at full power. And they probably had to orchestrate resetting the whole power grid. So that was not as big a one as 1859. We still worry about that the radio interference, that it could interfere with the power grid, that the internet might be interfered with. We still think about this. We're still worried about it. Probably now more than ever. The timing of the eclipse, April 8th, 2024. It won't be a day early or a day late. These times are for Burlington. We're in Montpelier here. It's a touch different. Not a whole lot. Just a bit. So that partial will start at 2:14 in Burlington, probably 2:15 here. There's sites on the internet where you can look up exact circumstances for you. So that partial eclipse will last for 1 hour and 12 minutes, and totality in Burlington will start at 3:26. And for 3 minutes and 15 seconds in Burlington, the sun will be completely behind the moon. Here, I looked it up before in Montpelier, you've got 1 minute and 35 seconds. It's shifting quickly down here, away from the center line. There will be literally some difference between the north side of town and the south side of town. The farther you get north from here, the more you'll get. If you get to North Calais, you'll have 2 minutes, 11 seconds is what I read. So even going that far gets you more. But 1 minute and 35 seconds is still pretty good. And in 1932, people came to Burlington for a 1.5 minute eclipse. So don't think you're getting gypped that bad, but it's a little, you're sort of getting chiseled down here. It'll be followed by a slightly shorter partial eclipse. We'll learn why in a little bit. That partial will end at 4:36 or maybe 4:37 here, and then it's done. Don't get on the Interstate 89. So the total duration of the eclipse, 2 hours and 23 minutes, the partials and the total together. Here's the path of the total eclipse through North America. We call this the money trail. Yeah. This eclipse will start way in the South Pacific, way south of Hawaii. The eclipse will hit the west coast of Mexico and travel through the United States from the southwest to the northeast. It exits off the coast of Newfoundland and travels for 1,500 more miles out into the Atlantic Ocean. The entire duration of the totality, from when it first hits the Earth until it leaves the Earth, is 3 hours and 15 minutes. And it will travel 9,200 miles across the face of the Earth. This curve that you see is a distortion of mass. It's traveling at a straight line. This is like a Mercator projection. So you're trying to balance a curve with a flat thing, and you end up with another curve. What else can I tell you? Down here, in this area, they got 4.5 minutes. We don't get quite as long. At the center, we get about 3.5 minutes. And that's because that eclipse is constantly moving faster. Here's more of a close-up of the area in the northeast of the United States, coming through southern Illinois, Indiana, touches Kentucky, Ohio, Pennsylvania, New York. It picks off a piece of Michigan, New York, Maine, New Hampshire, Vermont. Down here in southern Illinois, these people are really lucky, really lucky. This is their second total eclipse in less than 7 years. This was the intersection of the eclipse in 2017. So they get 2 of them in under 7 years. Here's the eclipse in Vermont. The blue line is the center line. The red line here, in this instance, is the southern limit. The northern limit is all up in Canada. We don't have to worry about the northern limit here. There's your center line. It comes in off near the north side of South Hero Island. The center line leaves up by Richford. Here's Montpelier. You're getting about 1.5 minutes. St. Johnsbury, about 1.5 minutes. Middlebury just gets nicked. Barry sort of just gets nicked. We're going to notice that you get 3.5 minutes here, you get 3 minutes 15 seconds here, and you lose 2 minutes by the time you get to Montpelier. And by the time you got 1.5 minutes here, and you got nothing here. It falls off quicker and quicker. It's the mathematics of 2 curves, not linear. Here's a more detailed map of the eclipse, of the timing of the eclipse. So here's the center line. right here on the north side of South Hero Island, 3 minutes, 34 seconds. St. Albans is on right near the center line. They're making a big deal out of it there. 3 minutes from here to here, they only lose 4 seconds. 4 seconds in all this distance. From 3 minutes and 30 seconds to 3 minutes and 15 seconds to Burlington. Virgins is at 2 minutes and 20 seconds, so it falls off quicker and quicker. 2 minutes in Bristol, and by the time you get here, you get to nothing. So here you got Montpelier, you're at about 1.5 minutes. But you can imagine, even here on this scale, there's a difference between the north part of Montpelier and the south, because it's falling off quicker and quicker. 1.5 minutes is still worth getting. Don't hesitate to be out there. What causes a solar eclipse? The moon gets in front of the sun. Simple as that. But it doesn't every time it goes around the sun. And it doesn't completely just because it's in the middle of the path. There's other things getting involved with all this. So the top one here, there's a sort of picture of a total eclipse. Here's a picture of a partial eclipse. Here's a picture of an annular eclipse. An annular eclipse, the moon is right in the pathway of the sun, but it is not a total eclipse. It's a variation of a partial eclipse. And we'll find out why in a minute. Here, the entirety of the moon's shadow manages to make it to the surface of the earth. If you're in this grayer zone, you're in the partial eclipse. We call that the penumbra. The center is the umbra. And in the umbra, you get a partial eclipse. If the moon in its orbit is farther away from the earth than closer, the umbra peters out before it gets to the surface of the earth, thus leaving this ring. And this ring is enough that you cannot observe the prominences or the corona of the sun. You cannot look at this without a filter. It doesn't get nearly as dark. When you're looking at a total eclipse, the sun is essentially down. It's not quite as dark as nighttime, but it's not light out anymore. You can't say it's light out. You can start to see some of the brighter planets in the sky, maybe a couple of brighter stars if it's a clear day. And you can look directly at that without a filter. In fact, if you try to use your filter glasses to look at the total eclipse, you will see nothing. There isn't enough light left to hurt you. There isn't enough light left to get through those filters. This will be about roughly as bright as a full moon. And 1% of the exposed disk of the sun is 1,000 full moons. And you can't look at that without your filter. Here's why we don't get an eclipse every month. Here's the plane of the Earth's orbit, and the plane of the moon's orbit around the Earth is skewed. Sometimes that moon is above the plane of the Earth, sometimes it's below. I really don't like these pictures. They're just total distortions of what reality is. The sun is way bigger than the Earth. The sun is way farther away than this picture, and the moon is way farther away than this picture. This is when I get the audience involved, and I need a participant from the audience to help me. Who wants to help? Okay, you're the first one to raise your hand. Come on over here. Stand over here. Are you familiar with Atlas?
No.
Atlas is Greek mythology. He's like a Greek superhero. And he held up the earth, just like I'm going to ask you to hold up the earth. Yeah, I had my wife do this for me. I'm like, I need to have things in scale. So what I've done here is 1 inch is 1,000 miles. So this is the Earth. This is the moon relative to the Earth in scale. And this string represents the distance. So you got to do two things. Hold that string on the Earth, okay? Hold it tight. We're going to see exactly how this all looks in scale. 1 inch is 1,000 miles. So how far, anybody want to guess how many inches of string I have here? Should be an easy math problem. I got 240 inches of string, because that's roughly how far the moon is from the Earth. So this is the true relationship right here. And sometimes that moon is up here, and sometimes that moon is down here. You don't get any eclipses. Sometimes that moon is out here. You get an annular eclipse. But this time, the moon is going to be more like this. And thus it's a little bit bigger in our sky and is able to completely cover the sun.
Is the moon either one of those three places, or does it go between them?
It goes between them.
Okay.
Yeah, but it has to be, pretty close. Yeah, you're right. Every month it's a little different. Occasionally we only get a partial eclipse without any center at all, but those kinds of partial eclipses usually just happen at the poles. They don't happen somewhere in the middle of the Earth. But yeah, I like to do that because it puts it all in perspective. And this is when I go on a tangent for a moment, because I'm kind of a nut. Thank you very much. I'm kind of a nut about the Apollo programs. I wanted to talk about this for just a moment. So on those 9 missions to the moon we did with the Apollo back in the late 60s and early 70s, we went all the way out there and back. Our space station, on this scale, is 1/4 of an inch. That's it. Except for those 9 Apollo missions, the farthest we ever have gotten from the Earth is less than an inch, 7/8 of an inch. That's it. The scale I just showed you, the sun is 4 times this distance. That's how big the sun is. And that sun is 1.6 miles away from here. So that is the scale of what we're talking about. I like to mention that we sometimes hear in the news lately about the Voyager probe. And the Voyager probe was something we launched in 1977 to explore the outer planets. And we're still talking to it. That probe on this scale is 230 miles from here. And we're still talking to it. But that's why I really don't like those pictures.
I thought we just lost contact.
It was still broadcasting, but it was like unintelligible. We were hearing it, but it didn't sound right anymore. They're working on it though. They think they've got some information that might straighten it out. But just getting the signal from that far, we've got to learn something just from getting the signal. There'll be something we'll learn. Here's another distorted picture. But this is interesting stuff a little bit. In reality, you can put 109 Earths across the face of the sun. You can put 1.3 million Earths inside the sun. And you can put 400 moons across the face of the sun. The sun is 400 times the moon diameter. You can put 400 moons across the sun. And the sun is 400 times farther from the Earth than the moon. So the sun is 400 times farther away and 400 times bigger. Thus, they match up in size. And it's kind of a catbird seat in the whole solar system. At no other place in the solar system will the planet's satellite match so closely the sun. in diameter, in apparent diameter. We photographed eclipses on Mars. We got pictures from Mars of the sun from Mars with the little moon passing in front of it. It's a partial eclipse because the sun's way bigger than its moon. We've taken pictures of eclipses on other planets, particularly on the planet Jupiter. Sometimes we see 2 at once. Every once in a while we'll see 3 at once. I think the Juno probe is now taking pictures of the surface, or the cloud surface of Jupiter, from the orbit of Jupiter, of an eclipse going on there. But there, those satellites are way bigger than the sun. They don't match up so closely. They wouldn't offer anybody there the opportunity to study the sun like we have. There's a diagram of the moon casting its shadow on the Earth. And that little black spot, that's the totality. This grayer area is the penumbra. This is the area in which you get a partial eclipse. Everybody outside of that totality on the lower 48 will experience something of a partial eclipse. Hawaii experiences a partial eclipse. Alaska barely gets nicked. They're kind of left out on any of the fun. That being said, in 2033, Alaska, in western Alaska, they have a total eclipse in 2033. Here's why the times change. This is how fast the shadow is moving. So it hits Mexico at 1,500 miles an hour. It enters the Vermont at better than 2,500 miles an hour over at the islands. It hits Burlington at better than 2,600 miles an hour and leaves Vermont at 2,800 miles an hour. And by the time it gets to Newfoundland, it leaves the coast of Newfoundland at 4,700 miles an hour. And that's because you're projecting that on a curve again. So that eclipse is moving in a straight line, but because it's on a curve, it's a bigger and bigger distance all the time. And since it's running at the same speed, but expressing itself across the curve, it's got to make up a bigger distance. So we see it as going faster and faster. Some people, if they're in the right spot, they'll actually see the edge of the shadow coming at them. If you're in the right spot and you're paying attention, you might actually see that. These eclipses occur in patterns. So there's a pattern of the moon in the sky called the Saros pattern, where it traces an area in the sky every 18 years. The ancients knew about it. The ancients plotted it. If somewhere in the culture they saw a total eclipse, everybody wanted to know why. Everybody wanted to know why. And that could have been the seed of something in us to study that, literally. The Mayans, or whoever they were sun worshippers. I wonder why. You see Mayan pictures of the sun, they include the corona. How did they see that? There's only one time you're going to see it, during a total eclipse. Oh, wrong button. So here you see the August of 2017 eclipse that we remember. Here's the August of 2027 coming up. Almost the same pattern. Here was one in July of 2009. Almost the same pattern. You see similar patterns down here. This is because this pattern reoccurs, but it's not in sync with the Earth's rotation. Here's that intersection in southern Illinois, but you know what? We don't see that over here anywhere. But, you know, some places get them more often than others. There's 2 solar eclipses a year. They don't have to be total eclipses. In fact, next year we don't get a total eclipse. I've been looking it up. I've been telling people we get one every year. Not true. There's years off. Next year we'll get 2 eclipses, but they won't be total eclipses. They'll be annulars or partials. On average, the Earth, any given spot on the Earth, on average, will get a total eclipse every 375 years. Average. There's places that wait a lot longer. There's places that get them more often. Our last total eclipse in Vermont was in 1932, 92 years ago. Our next total eclipse in Vermont, the rain date, is May 1st, 2079. It's more in southern Vermont. The next total eclipse in northern Vermont is 2106. So obviously we're getting them more often than every 375 years. But it's not an easy thing to wait for the next one. The next one I'm trying to think how this goes. There's one in Canada in 2044. The next one in the continental United States is in 2045 in the southern states, United States. So this will be the last total eclipse in the lower 48 until 2045, another 21 years. So anybody born during this eclipse will be old enough to drink for the next one. Where are we going to look? Look now, if you got a clear day between now and April 8th, look where the sun is in your sky at about 3:30 in the afternoon. It's going to be pretty much the same place. So if you know where the sun is for the next 2 weeks, you get an opportunity to see the sun at about 3:30, and you can see it from where you're standing. You'll be able to see it from where you're standing if it's clear, not if it's cloudy. When the eclipse starts, the partial phase starts, the sun will be 49 degrees high. When the totality starts, it'll be about 40 degrees high. When the partial's over, it'll be about 30 degrees high. This is the whole eclipse. But really, the show is the totality. I've witnessed 2 partial eclipses in Vermont since 2021. June of 2021, we had a sunrise eclipse. It was covering about 70% of the sun as the sun came over the horizon in June of 2021. We had one last October that only covered about 20%. The next partial eclipse will be in 2026 here in Vermont. That'll be a total eclipse in the Arctic. But here will be a partial eclipse. The partial eclipses really just don't get our attention that much, do they? Because they're really not nearly as exciting. It's interesting to the astronomers. We want to see it. We like to see it move, all that stuff. But the public it's hard to get them excited about it. What will happen when the totality hits? The sky slowly gets dimmer a bit during the partial phase. There's a big difference between the beginning of the partial and the end of the partial. You'll notice it. If nobody told you it was happening and you were totally ignorant of it happening, you might not until the totality hits. And the totality is abrupt. It's not instantaneous, but it's quick. It's abrupt. There's a definite change in the temperature. The temperature could go down by 20 degrees. You'll notice the wind change because it's affecting, just like when the sun goes down, you sort of get that quiet period when the sun goes down. The animals will react. They'll think the first shift is off and the second shift is coming on. In 2017, I was there in Kentucky to observe the eclipse. That being said, I did notice flocks of birds heading for the trees. And I wasn't really paying that much attention. I knew to look, but that's not why I was there. We're animals too. We react pretty amazingly. You'll hear a lot of hooting and hollering with the totality. That's one of the ways you know you're in the totality. You'll hear everybody hollering. I like to do that thought experiment where I'm some Stone Age guy out hunting and gathering, doing my thing, not paying attention. And then all of a sudden, pretty darn quickly, It's like sunset way in the middle of the day, and I look up and I see a big black hole in the sky. Right? I won't say what somebody yelled out in the audience. Here's a time lapse of the eclipse. So this is everything in the sky rises in the east and sets in the west. Everything's going from the east to the west. The sun is going from the east to the west. The moon is going from the east to the west, but the moon travels at a slightly different rate because it's going around the earth. So that rising and setting is somewhat skewed relative to the sun. So the sun is moving to the east relative to the sun. So you'll notice that shadow starts to clip the sun here and gets bigger and bigger until we get to the totality. And then it goes the opposite way as that partial phase comes to a conclusion. The difference between the sunlight between here and here is almost nothing. You really won't notice it. You might think you see it, but it'll be one of those things. Do I see it or don't I? You'll want to think you see it because you know it's happening. As it gets here, you'll start to see it. You'll start to see it, but it's still casting shadows. You're getting full shadows. It's casting shadows till the very end. That's one of the ways you know the totality is there. You're going to quit seeing your shadow. This is more of a Photoshop one because the distances are bigger. This was taken by one of our members, Steve Yerby, and he went to Madras, Oregon to see the eclipse because it was much more of a sure bet there than anywhere else. That was one of the hot spots. You need filters on your camera to take pictures here and here. You don't need a filter on your camera here. You don't need any filter. Yes?
So at that point, we can take our glasses off
Yes.
and then just put them right back on after 2 minutes.
When you'll know.
Okay.
You'll know. We'll talk about that a little. Everybody wants to ask me, how do I know? How do I know? How do I know? You'll hear everybody screaming and hollering, and that's one way you'll know. You'll know. You'll know. I can guarantee it. Having witnessed one, it's real obvious. At that point, no filters. Up until that point, filters. When that's over, filters. We all get popped in the eye a little bit, don't we? If we drive a car in the sunset, what's happening to us? We're getting it in the face. If you've played baseball and you're in the outfield looking for that ball in the sun, what are you getting? You're not getting it straight in, but you're getting it in the eye. And if that's making you look away, it's too bright to look at. When you're looking at the totality, you will have zero inclination to look away. There will be nothing that will cause you discomfort. That's one of the ways you know. If it's comfortable to look at, you got no problem looking at it, you're okay. I always like to say, if you're looking at it when you shouldn't, you're not being a bad guy, you're being a dumb guy. Okay? That's a good way to look at it. It's like, I was at a rattlesnake museum in southern Texas, and the guy gave me a statistic on snake bites. He goes, what's the statistic on being bit by a rattlesnake? I'm like, I don't know. He goes, it's like this. He goes, males, ages 18 to 36. And you hear, hold my beer, watch this. It's the same here. Same effect. At the very end of the partial phases and the very start of the partial phase, you get this effect. Bailey's beads. And what this is, it barely lasts at all, is the last vestiges of the solar disk shining through the peaks and valleys of the moon. So you get this lumpy effect. So here the sun's totally covered, and here's a little lower elevation area on the moon, letting more of that sunlight through. Bailey's beads. Remember that. I won a Trivia Pursuit game once because I do that. The diamond ring. A few seconds before totality and a few seconds after. You really ought to be looking through your filters at this point. You really ought to. You'll be tempted not to a little bit. Just don't look directly at it. And I don't want to be hearing from Harding and Desai. Okay, use your head. You really shouldn't be looking at this, but this is really the last vestiges of the partial eclipse, and your sign at the end of the total eclipse that you should not be looking at this anymore without your filter. When you hold your filter up to this, you will see the light coming through. During the totality, you won't see light coming through your filter. Here's a picture of the 2017 eclipse taken by one of our members. I remember, that little orange spot on this picture is a solar prominence coming off the sun. I remember seeing that. Took a real quick look through my binoculars at it. You can look through binoculars at a totality. Don't take forever. You certainly don't want to be looking through them when it's all over. You're concentrating the light into your eyes. But at the start of the totality, we've got adults here in the room for the most part. You can take a quick 10-second look. Don't belabor. Don't be caught looking through those when it's done. The club has placed telescopes in some of the Vermont libraries, and we've told the librarians, don't be lending those telescopes out for this eclipse. Make sure you get them back. Don't lend them out for the eclipse. We got signs all over them. Don't look at the sun. Don't look at the sun. But, no. On this picture, you can see Venus down here, this spot. You'll be able to see Venus and Jupiter during the totality. And we'll get to that in a minute. We've got another picture. Here's a closer view of the sun during the totality. And that white area, that's the corona, that's the atmosphere of the sun. You cannot see that without a total eclipse. That's this thing when you see a picture of the Mayan sun, you see that, right? How did they see that? They had to see one of these somewhere. Here's a picture of the night, not the night sky, of the sky during the eclipse. So, here's the sun being eclipsed. Right here, this little spot. See it? Right above my red line? That's the sun. Here's Venus. Here's Jupiter. There's a star called Rigel. You might see a couple brighter stars. You'll definitely see those two planets if it's clear. It's like a half an hour after sunset. That's the way I describe it. At least that's what I saw in 2017. This eclipse is supposed to be a little deeper. The sun is more in line with its nearest approach to the Earth than in 2017. So this eclipse will be a little more intense. We'll be a little bit deeper into the shadow. It'll all depend on what the day brings. Supposedly, we may get a glimpse of a comet. There is a comet, Pons Brooks, out in the neighborhood. The question is, will that comet be bright enough? Most indications are the comet is not bright enough. But the comets are notorious. They are notoriously hard to predict how bright they are. And if there's an outburst on that comet that spews all its water vapor out, so there's a bunch of ice and water steaming out around it, it may catch more of that sunlight and we may see it. I would say that's maybe a 10% chance. But if you have an opportunity, you've got to try to take in a lot during your 1.5 to 3 minutes. You've got to try. You're going to look at that sun, you're going to look not at the sun, you're going to see the sun's corona, and you're going to be mesmerized by it. This is totally off scale as far as what you've ever experienced. But you're also going to try to look around that. And you may see that comet. You may not. Probably not. But you don't know if you don't look. If you got a view of the horizon, Saturn and Mars will be down on the horizon. They would be bright enough if it's clear enough, and you got a view down on the horizon. But you should, if it's clear, you'll definitely see Venus and Jupiter. I certainly saw, yes.
Where will the comet show?
Between the sun, above the sun, between the sun and Jupiter, in this area here. This is a program called Stellarium. You can download this for free onto your computer. Astronomers are a pretty friendly bunch. We give a lot of stuff away other people will sell. And you can get this program. And what you can do with the program is you can look any place on the earth at any time and see the sky. So these stars, these planets, these stars that you see, you may see them during the eclipse because the sun is blocked out. But you could never see those stars normally. 3 minutes after you advance the program, 5 minutes, you don't see this anymore. Right? Safe solar viewing. We want to do this safely. Life doesn't get better when you don't see right. Never look directly out the sun without a filter. Simple as that. You can look at the sun's image indirectly by projecting it onto a piece of paper. You can look at it like this. Have a tiny little pinhole in the paper and project onto another piece of paper, and you'll see a small image of that sun. So if it's in that crescent shape of a partial eclipse, you'll know it. This lady's over here, she's one of the librarians in Jericho, and she's grinning looking at it, and you'll see why in a minute. Because our club president over here punched a bunch of holes in the paper that says Vermont Astronomical Society. And every one of them is a little crescent. You can just literally make a hole with your fist and shine it on a piece of paper and probably get something. This guy punched a triangle. I guess you can kind of see it, but the bigger the hole in the paper, the fuzzier the image will get. This guy just literally held up a big white hunk of cardboard and let the light filter through the leaves of the trees. And every one of them is a little crescent.
Oh, wow.
And one of my presentations, somebody yelled out, "Yeah, right." He's going, "No, that's right." Because the leaves are never out on the trees before May in Vermont. You can take a box and punch a hole in one end, have a piece of paper in the other, and this guy, he cut a slot in the box, so it's a little darker inside that box, and you can see it better. You've got better contrast. This guy made one where you can just stick his head in the box, keep it nice and dark, so you can see it better. Eclipse shades, eclipse glasses, they're everywhere now. Mm-hmm. Everybody, I bet, has some already. If you don't have them, we got some for you. Okay? They should be approved glasses. We'll go over that in a minute. But eclipse shades, you can certainly do it with that. You need to know you need to take care of these a little bit before the eclipse. You don't want to crease them. You don't want to scratch them. You don't want to bend them up. Keep your fingers off the lenses. I tell people put them in a dictionary under eclipse. Here's some ways to view the sun. The exception is this one. We'll talk about this one in a minute. Here's your viewers. This is more like the club bought a card with a piece of that material. Just hold it up to your glasses or your eyes. You can pass it on to somebody else. You won't have their COVID germs on it as much. Here's a fancy one for a telescope. Here's one of a pair for binoculars. Here's some fancier glasses that are, not just throwaway glasses, they're better. Number 14 welder's glass. One of the biggest debates there is in all this. If you look through a number 14 welder's glass at the sun, you'll say, oh, that's fine. That ain't so bright. In fact, that's great. But we are unsure if it's blocking all the spectrum of the sun that needs to be blocked for your eyes. Certainly the visible intensity is fine. But we are unsure of whether or not that ultraviolet is getting out of there completely. So we're telling people, don't do that. Don't do that.
No unexposed X-ray film.
What's that?
Unexposed X-ray film.
Don't do that either.
Well, we did that when we were kids.
Well, we're going to get to that. We got a whole list of don'ts. We got a whole list of don'ts. Yeah, right. Yeah, but no. Here's ours. Here's a picture of ours. So we got them on a card. And you can just hold it up to your glasses. That way you can pass it to somebody else. And if you got some little kid, you don't have to worry about all the stuff on it. Yes?
So I have one of those, and I wasn't sure that white strip, that stay on there? Can you still see through it?
Oh, yeah. And, you know, this is the front, that's the back. You can hold it either way. I always point the mirrored surface toward the sun. That's what I do. Yeah, you'll see through that. You'll see the light of the sun through that. You won't see anything else. If you got one of those and you got a clear day tomorrow, you can hold it up to the sun and look at the sun. If you got a big honking sunspot, you'll see it. A big one. Notice here, there's a little ISO number. We'll get to that. Right down here, you see ISO, International Standards Organization. During the partial, you don't need a filter. During the partial, you need a filter. During the total, no filter. This pretty much goes for your phones, too. If you're trying to take a picture of the partial with your phone, you may burn out the sensor in there. I don't know. Depends on your phone, but I wouldn't point a phone at it, not without a filter. During the totality, you can point your camera or your phone at the totality and take a picture. I told my wife when we were in Kentucky for the 2017, take a picture of the sun, take a picture of the surrounding area, so we have proof that we were there. Don't be taking a bunch of pictures, I told my wife. I saw a guy in 2017. He tells me, I have been to 6 total eclipses and never saw one. I'm like, what are you doing? He goes, look at all these cameras I got. I'm using these cameras. I told him, why don't you leave the cameras home the next time? Experience it. There will be more pictures for you to look at than you have time left to look at. You know, we got guys in the club who will be taking pictures. That's okay, but don't spend all your time taking pictures. You've got a lot to do in a minute and a half or 3 minutes, depending on where you're at. Trust me. Here's the ISO number. ISO 12312-2. This 2015 is just when they set the standard. International Standards Organization. They block all the stuff that you aren't supposed to look at.
Do the glasses,
What's that?
degrade over time? Do the glasses degrade over time?
No, but they can be damaged. Okay, so if you got a pair that you stored nicely in 2017, you can use them. If you got a pair that's in the bottom of your junk drawer being scraped by pencils and pens, throw them in the garbage. It all depends on how you take care of it. Ordinary sunglasses. It doesn't matter if you put 10 pairs in front of your eyes. No polarizing filters made for cameras. No smoked glass. No photographic or X-ray film. Got your name on it. None of these potato chip, myelorized potato chip bags. No CDs, no DVDs, no space. Don't do that. You will be sorry. You will be sorry if you start doing that. You know, not many people will look at the sun long enough to hurt themselves. But they will if they try. You're really not, if you follow your head, you follow your instincts, you'll know when to look and when not to. Don't force it. You wreck a lot of things trying to force it when it shouldn't. No welder's glass. No welder's glass. At least that's what we're telling people. You'll find other people who will say other things, but the club doesn't want to get caught. We're telling people, no, there's plenty of viewers. Plenty of stuff out there for this. Here's a guy using binoculars with filters on them. Notice that the filters have to be on the front of the device you're using, not next to your eyes after. If you put them next to your eyes after, you'll burn a hole in them. Just like you could start a fire with a magnifying glass. Put them on the outside. Even your glasses, theoretically. Okay, even your glasses. So this guy's got them on the outside. I don't see it. He's the only guy you can really see, but that's enough. You put him on the outside. Notice he just bought filter material and taped it down to the front of those little lenses. That's fine, as long as he was careful with it. Here's a telescope with a fancy filter on it. I like to point this out in case anybody's got a telescope they're going to use. You really don't need all this telescope to look at the sun. The sun's pretty bright. You don't need all that light. But if that's what you got, that's what you're going to use. Notice here is a little mount. That's for a sight scope, kind of like a deer rifle has. And you want to take that off. Because if you don't, somebody will invariably come up to your telescope and look through it. Not only that, if you got one of them sight scopes with a reticle in it, you'll burn it off before the eclipse is over. You'll throw it away. It's garbage. So if you got one of them on your telescope and you're using a telescope, either take it off or cover it securely with a sock. Tie it on. Don't let somebody look through that. They'll screw themselves up. I like this website. This one's been around forever. You know, if you were to look up these guys 3 years ago, they were already out there. They're now like 7 or 8 down on the list if you Google Eclipse. But I'm familiar with this website, and I like it because you can look up any community in the state or the country and see how much time you're getting. If you're in a partial, how much of the sun's going to get covered. You've been to tundras. You're not getting totality here. You got to go north. You know, but in there they told you, 99.1% or whatever. The reason you're here for our video. So one of our club members, Paul Walker, took a video of the eclipse. So the first part is the actual part of the sun, and then he repeats, but it's not of the sun. It's the area around it. I think it's even more fun. It's more fun. So let's see if this works. Okay, here we go.
Yeah, we're going to be mostly clouded out, folks. Almost there, folks.
Still should have your glasses on.
Glasses off! Glasses off! Look at that! Look at that! Look at that! Look at that!
Don't laugh at that person. You're going to do the same thing.
Oh yeah, look at the horizon. You gotta The horizon looks like a sunset. Okay, we're coming up on the halfway point, folks. Oh, through the scope. Oh, gorgeous.
So see, he's looking through his scope at it.
Are we looking for this?
You can do that, but you better be careful. You don't want to be looking when it's done.
There's no more than we had. There's some there, but
So what's that?
it's still
Is that?
It's the camera.
absolutely
No, it
gorgeous.
looks like it's,
There's clouds.
It is cloudy.
Oh, yeah.
Clouds.
It is cloudy, okay.
Yeah.
It's startling. It's absolutely startling.
Oh,
That's
glasses on.
on.
Yeah, especially now.
Dive in.
Beautiful, beautiful, beautiful. Look at that.
See, now you can see he's looking through a filter. You can already see it.
Something. That was
Not
something.
be looking at that. Right. Switch.
Yep.
I like this better. Notice there's a guy down the block. He just turns his lights on. He's not even outside. Watch this. That's how quick it gets dark.
Glasses off. Glasses off. Look at that. Look at that. Oh, yeah, look at the horizon. The horizon looks like sunset. So we're coming up on the halfway point, folks.
This guy turned on his lights.
Glasses on. Yeah,
You can
especially
see the
now.
bands going on the ship. I'll talk about that when it's done.
Beautiful, beautiful. Look at that.
Now here comes the shadows are coming back. It's time to put them glasses on.
Look how quickly it's brightening up. Wow.
Yeah, it's rough.
This is a strong night. Oh, we're watching the shadow bands. Look.
So he's talking about, he's noticing a white sheet out there. You can't really see him in the video too well. Put a white towel or a white sheet on the ground.
Big band.
And the effect you get at the very end of the partial, and when that partial starts again after the totality, you're going to have bands of light and dark moving across that white sheet. And what's causing that? A star will twinkle. When you look at a star, you see a twinkle. When you got a band of light from the sun, that's that narrow band, even though it's curved, you're getting that same effect as the twinkling light. And if you have that sheet on the ground, you're going to see that moving across the sheet. It's one of the things everybody can do. One of the extra things. I always like to talk about in the modern century for the eclipse. When we had Einstein talk about his theory of relativity, it was a conjecture. He wrote this up in a book. It all sounded good. We couldn't prove it. None of it could be proven, except during a total eclipse. One of the hallmarks of relativity is gravity bends light. And during a total eclipse, they took pictures of the surrounding stars and remeasured their relationships, and found that the stars were pulled in toward the sun just a tiny bit, proving that the gravity of the sun was bending the light from the stars. We now had a smoking gun for relativity. They still do that, I'm sure, in science classes. Things they're going to be doing for this eclipse, studying the corona. They are big on studying the corona because we still don't know why it's so much hotter than the surface of the sun. We know the corona is 1,000,000 degrees and the sun is 11,000. Why is it so much hotter? We're going to study the corona. We're looking for these coronal mass ejections. What else are they going to look for? They are looking to look for asteroids really close to the sun. They want to find them really close to the sun. I think I know why. Most asteroids are balls of ice. Any asteroids that close to the sun are going to be balls of metal. Which ones are more valuable? I'm guessing. You may not want to know now, but they might want to know in 100 years if they can find them. And they're going to be looking for asteroids real close to the sun. Any questions?
You said that we could, it's the one time that we can